very good evening, everyone. So today we will discuss about Headroom. The Headroom. Uh, Previously, I was working on Headroom, right? As you all, I think, aware of it because I also made some changes in your I've given some bat files to run, so which actually made some changes, but you don't know exactly what exactly happening behind that, what exactly doing by the Headroom, right? So Headroom, starting with the what exactly Headroom is. So we'll slowly deep dive into like how it exactly works and what is the use of Headroom and what exactly it helps us to in what extent it will be helpful in our projects or our daily uses. So let's start. And Coming to the very basic to the Headroom. So Headroom is the context optimization layer for LLM applications. So like every day you use ChatGPT, Codex, or any other cursor or Claude code, right? So every time you give some task to the agent, so it performs some tool calls, or it makes some general prompts, and it makes your work done, right? So it takes control of your laptop, or so it takes your project's control, and it makes some new code, or it debugs your existing code, and it makes a new application, everything, right? So this all complete thing will be run by agent, and it mostly takes most of the tokens. So you just give the command, and it keep on running. You don't know exactly what background it is running and how many tokens it is taking, how much cost it is actually happening per request you are giving to the agent. So here we will cover how we can able to make it optimized, so that we can able to get the same accuracy, and as well as we can also utilize, or we can reduce our cost. So yeah, in this session we'll concentrate on why we used to use the Headroom, and going forward, what are the before what are the before solutions which proposed before the Headroom is introduced, and what is exactly Headroom is, the in or not in a single sentence, but we can also deep dive what internally it is happening, and then moving forward to how internally the what exactly models it is used in Headroom, so which makes our flow easier and run only within our computer. And we can do some hands-on experiments on how we run the Headroom in our personal projects, or else to integrate into our codex or any other coding uh, ChatGPT or Codex kind of platforms, and also the reality check, how extent we can use the Headroom as well. So coming to the first one, like why the context window is not the bottleneck, and what you put in it is. So what it means is as you all know what the context window is like. So when you keep on giving the prompts or the chats to the agents, the history, the prefix chart, everything will be saved, right? So what we know is when we keep on giving the questions, it already saves that content, and it will read that, right? So exactly it happens, but only for certain limit. So, and it takes lot of data, right? So for every request you give, it takes a million of tokens. Again, if you keep on continuing the same chat, it takes again million of tokens. So this keeps on going to some extent. And so instead of giving those many tokens, we can reduce that, and we can use small chunks, so that it can able to utilize for the further prompts which is given by you, or and it can make utilize more better way. So here, the four things we mostly focus: the cost. Has if we reduce the every token you pay for it. So every whenever you give some prompt to the agent, it takes a lot of tokens. So every token you pay for it actually. So that token actually counts, which comes to your final billing to your coding agent. And the latency. So if you keep on giving the long prompts or a long history of one single chat, the prefill will be always increasing, right? So instead of keeping the unnecessary data in the prefill, so which makes your latency also increase. So the some coding agent has to read the previous chats also, and it takes lot. It keeps on increasing the time. So that comes to the latency, and also coming to the accuracy. If you keep in the same way, if you keep on giving the prompt, the accuracy also decreases, and the ceiling at one certain limit. So the agent will there is a system where it cuts to the some particular point, and it only takes the last k chat which you are given to the agent. So based on that it will take as a data, and it will analyze your like whatever the prompt you have given to the latest. So where the tokens actually go. So if you build a chat app, it and the user writes the prompt. In an agent, the tools do, right? So and what they are far less consist. So when you are building a chat app, and like you give a prompt, so what are the like tokens, where the tokens are exactly taking much time. So much tokens are taken in this. So in this chat, you can see the system prompt takes like 4%, and the chat history it's like 9%, and the RAG chunks, if you are like using some RAG kind of systems, it takes like 13%, because RAG is nothing but a a retrieval model. So when you have a huge data of in your DB, if you want only certain chunks of data which is relevant to your prompt. So the RAG is a system which only gives those relevant data. So you can restrict with some k number of top chunks. So you can define that, like if I only want five chunks which is relevant to my prompt, and it fetches only those five relevant chunks from your data set. So instead of giving a whole data set, the RAG system will work in that flow. So mostly this RAG is used for the chatbots. So we don't go deep dive into the RAG. So and we'll discuss some other time. And next, the file reads, it takes like 16%, and most of the time, like most of the tokens taken here are the tool outputs and the DB rows. So it is like 58%. So there is a 500 row problem. A single search or select returns 500 near identical JSON objects. The model needs three of them. You pay for all 500. So this turn on every turn after it. So because the tool result stays in the transcript. So what does it mean exactly? Like you want only the three rows of data, but when you make some select data or any search operation, it gives all 500 rows. So you don't need you don't exactly need those 500 rows. Only the you need those three rows. So but you need to pay for that all 500 rows. So this exactly increases your cost, and also unnecessary data into your prompt, like unnecessary data into your tokens actually. And there are six things teams already tried. So one is hard truncation. So the tool will cut n characters, as I told. So when the chat, when you start a chat and you keep on giving the prompts to same one chat, and it reaches to one point where it only takes the last n. The n is defined by the coding agent, which it is inbuilt. You know, you won't be defining it. So, and it takes only those n characters, and it will take that as a data, and it gives to the like model, whatever the provider you given to. So in this way, you will be lost the exact other characters. So like other previous history will be lost. This case will be happening every time. But here the thing is, we can reduce using the headroom actually. In headroom, we will compress everything, right? So we can also utilize those previous charts. And next one, like there is a rolling summarization. Ask a LLM to summarize whole terms. So it is similar like uh, instead of like model to hallucinate, it will actually use the summarization of previous context. And there is a RAG over history. This system is like the same, the RAG method. I have explained the RAG system, right? So those RAG system will be present here. The only the relevant data will be coming. So based on those top k chunks, he will give the input to the model. So this is one system. And the prompt compression models, there are some other models which are actually present. So these are actually LLM models like LLM Lingua, long LLM Lingua, and select to context. These are the models which already built by some like provider. You can use these models to compress the tokens as well. But these are LLM models, not like these are heavy models. So to run in your system, it takes most of your RAM and your processing. And there is another models like there is a auto compressor and gisting. So these are also like having implemented, but there are some limitations. I will show you in the next slide. And there is a prefix or KV caching. So in KV caching, when when a prompt is given, when the task is running by the agent, so the KV caching will be save the data of your most previous request. So in that caching, it will store the data instead of like so when you have the relevant prompt again, so instead of again analyzing completely, the KV caching will be used so that it will hit the cache when it hits the same prompt in the cache, then it will utilize the same data. So here is the scoring prior art. So you can in this table you can see the what are the limitations over here. So hard truncation, you can reduce tokens, yes, but content aware, it won't be aware of content. So uh, there is a drawback over here. And reversible, so you cannot able to reverse when a compression is done. So you given the context like there is a log file, big log file you given to hard truncation. Again there you cannot able to reverse the data. So there is no extra LLM used here. It is like general logic they have written. And in rolling summarization, it reduces tokens, yes, and context aware it is partly. And is it reversible? No. So we cannot able to reverse the thing. And in the RAG history, you can do we can reduce the tokens. We can like there is a content aware because we are when a prompt is given, it will only give the relevant content uh, which are required from the dataset. And also it can be reversible, like if you don't want the stop gauge chunk, you can also take the other, you can write the code in that way. So but it takes the embedding calls, so there is a costly operation of embedding calls, so there is a drawback of that one. And LLM Lingua, uh, it can able to reduce uh, content aware statistically, and you cannot able to reverse. So in this way, if we take the headroom, you can make all of it. You can reduce the tokens. It has the content aware. It can be reversible as well. So if you don't like, there is a compression happened by the headroom, but the agent or the provider doesn't accept that compression. It understands like this is not enough. Then it can actually get back to the original content. So there is a model called CCR. So using that model, it can able to again get back the things. And there is no extra LLM we use in the headroom. We use mostly ML models, and there are like logical coding stuff. So there is no much use of LLM calls. So which reduces your RAM utilization and the CPU as well. So coming to a headroom, in single sentence, it is a compression layer that sits between your agent and the model. So and strings everything the agent reads before the model sees it. So it sits between your LLM provider and the agent. So whenever you give a query to the agent, it actually goes to your provider, right? So in between, we introduce our headroom, which actually compresses the whatever agent gives the input to the provider. Yeah, those data will be compressed in the headroom, and that data will be again gone to the LLM provider. So in this way, we will compress the data and we can reduce the cost, efficiency, and everything. So what gets compressed? So coming to the headroom, like internally, what type of data it can able to compress, and at what extent it can compress, we can able to view in this particular table. So first coming to the JSON arrays, so it can able to compress like 70 to 90%. So uh, JSON arrays are like you can take any like when you are doing a web application, there are like lot of JSON files, right? So to compress those JSON files, we can integrate Headroom. And for the logs, if you want to compress the log, if you instead of giving there are thousands lines of logs you can available. So when you are running a web application, you can see a lot of log files which are like exceeding more than 1,000. So if you had some issue or like any error in your application, and you want agent to make some to identify what exactly mistake is, it has to analyze complete log from starting point to the 1,000th line of that code, right? So instead of reading all the lines, why can't we just give the error line? So in the log files, there are like multiple other stuff which are irrelevant to the our prompt. So if I give the prompt like what exactly the error in this particular logs, so it based on this particular prompt, the headroom will analyze only to fetch the error particular lines. So it will truncate all the other lines, and it can reduce to the 80 to 90%, 80 to 95%, and it can give only those three lines of error to the LLM provider. So in this way, we can reduce the context and the search results. Uh, in the search results, you can like there is a RTK model, so it will be inbuilt used by the Headroom. So I will tell you in the further slide. So the RTK is nothing but Rust token, token killer. Uh, this particular model actually used in place of globe or grep, which we our agents will be used to find our results in the folder structure. So RTK will reduce that and get tips and plain text, images, source code. This all there are like percentages of experiment they have done and given these results. 30%, 40%. These are given by the headroom itself. And the climb measured. So there is like you can see here there are 100 log entries, one fatal buried at position 67. So in the 100 lines of log file, the error is at 67th line. So instead of giving 100 lines of that like entry, so we can only give that 60th, 67th line, right? So in this way, so we can reduce like 10,000 144 baseline to 1200 like 1200 to 1200 line. So in this way, we get LLM can understand in both ways, and it can give most of the correct answers. So they also tested it like correct answers are like 4 by 4. In the headroom itself, after compression also they got 4 by 4. It is like we can compress it like compress cost by 87%, 87%. And here the pipeline is deliverability short. So here how exactly headroom compresses the thing. So here there are like two main models used within the headroom. One is cache-aligner and the content router. So here cache-aligner reports the dynamic prefix drift like dates, session, context. So you can keep this static prefix cacheable. So there is a cache in the headroom. So whenever you give the long context, the cache will be storing those all the histories of your chat, and it can whenever there is a necessary, the cache will be hit, and the similar data will be given to the LLM provider. And there is a content router inspects each content blocks and detects its type and routes it to the exactly one compressor. So there is only one compressor model. So based on your input data, it chooses which compressor to choose. Like there is a smart crusher and code aware compressor, because our input contains lot of data, which can be plain text, which can be logs, which can be JSON. So our headroom will be analyzing which kind of data we are exactly giving, and based on that, the model will be selected and the compression will be done based on the compressor. So here are the like four main things. Uh, First one is detect. So there is a Magica ML model, so which pattern matching identifies the content type. This model is used to find the pattern, like which content it is coming, and the extract. A handler builds a structure marking what must survive. So it marks which exactly data need to be done, and the compress model compress stage, the which compressor which need to pick will be done in the compress, and it will store the like original data in the CCR cache. So when your compressor is not like well enough, then you can revert back to the CCR. So you can reverse to the original content which is given by the agent. So detection and routing. So here are if we have JSON errors, so we use smart connector. The savings is like 70 to 90%. And if we are like you having test logs, we will be having a log compressor, which is like taking this much percentage of saving. So for each type of data, we'll have each type of compressor. So this will be picked by Headroom itself. First, it will detect what type of data it is, and then based on that, it will be picking which particular compressor need to be picked. So yeah, coming to the smart crusher, so it scores, it does not slice. So it only scores what exactly data is. So here in example, you can see how many tokens are there before, like 40, there are 45,000 tokens. The results will be like in this way. Uh, After it will be 4,500. Let us say it is 90%. So it won't completely drift it, but it gives like there are like more 995 type 995 more files. So it gives in that statement rather than completely truncating it. The first stage it will context for pagination and recency, and error types 100% preserved. Anomalies if there are anomalous statistical outliers, and relevant items. If there are relevant items, there is BM24 or embeddings model will be used in it. So and the change points are like sudden shifts in running time. And CCR. So CCR is the main role in the Headroom, which can make your compression reversible. So in this particular CCR model, it is actually MCP model. So we can integrate in a MCP. It actually the abbreviation of it is like compressed cache retriever. The original never leaves the machine, and the model can ask for it back. So when a compression is done, so our agent will always be knowing what exactly made by the Headroom. So if there is a compression, there is a hash created in the internal cache data. So that in that cache data, you will be having the original data which is given by the agent. So if the ML model doesn't want the Headroom compression, if it feels the Headroom compression is not the worth data, then it can able to get back the original content. So in that way, the ML model can provider can decide in whatever the way it can. So the compression store, the original goes into the LR cache, and the hash keys will be created for each one. Uh, for injecting this tool, you can there is a like Headroom retrieve, and this is the MCP call. So when it can call this MCP, and it can get the original data itself. And resolve. So if the model calls it, the response handler intercepts, fetches the cache. So as it is fetching from the cache, so it takes only less time, like 1 millisecond. And track context. So across the context tracker notices when a new question relates to something compressed earlier and expands it proactively. So when there is a relevant content, it keeps on like expanding. If it founds like same data, it will take from the cache. So what else ships in the box? And what I like there are like cache optimization, persistent memory. Persistent memory is like when you have multiple charts, So the similar cache will be used for the persistent memory. So if I have done some chat in, like I've given some commands in one chat, and I've opened a new chat and want to make the same project related code in the this chat. So this persistent memory will be used to take the same content actually. So when you make the changes, made some prompts in one particular chat, and that data will be saved in the cache, and it can be utilized in the other chats as well. Coming to the shared context, so when you are not only working with this one single agent, you are working with multiple agents. Like if I used sometimes Codex, and I got there is a set of my credits, and I shifted to the like other Claude code or open code. Uh, there also there is a common cache, so where you can your previous data will be saved and can be utilized in the other agents as well. So that feature also available in the headroom. And the failure learning, so there is a failure learning. So it in the failure learning, it reads the past sessions, and like if the ML model calls, there is a CCR, right? So whenever the model calls the CCR, it thinks there is a mistake in the headroom, and it keeps on learning based on that previous data. And then the metrics, uh, there is a per request logging, cost tracking. There is a complete dashboard of this particular headroom, so you can track every request, how many tokens you are getting hit by the your particular prompt, and how many tokens are getting saved from this headroom. Everything will be done in the dashboard. So I will show you that in later. And then there is also MCP support. So MCP, you can integrate into your agent. So there are like three: Headroom compress, Headroom retrieval, and Headroom stats. So this every Claude Code, Cursor, any MCP client can able to access this MCP. There are four ways to adapt it. So one is like proxy. The other way is like using the Python language. You can also import the compress like Headroom from the Python code, and the in the TypeScript and any other framework as well. So this is just the like how you like integrate the Headroom in your particular agents and the projects. So this is how you can do it. Coming to the local setup, you can directly use UV, or else you can also use pip install headroom all. So when you use it, it completely integrates into your all the first it will integrate into your Anthropic, which is basically Cloud Code. So later, if you want to integrate in the codex, you can directly use the wrap. So headroom wrap codex can able to make the use of codex, the headroom in the codex as well. And also you can deploy in the Docker if you want. So there are like proxy, right? So proxy, when you start a proxy, it can directly you can ask integrate this URL to any your coding agent. So the headroom can be utilized using this proxy server. So local setup. So step two, run the proxy. So first you will run the proxy. You will assign the like those Claude headroom URL and to the particular coding agent. Here we used Anthropic. So in this way, if you define Claude will be assigning. If you are using OpenAI, this is the way you have to define it. So it will assign to that particular coding agent, and it will be used by the it will trigger the headroom, and the compression will be done. The pathway will be like it. The agent will be first to go to the headroom, and then the LLM provider. So this is the code, example code. So I'll just run it and show you. So first I want to do with the terminal. So I have already installed the headroom. So I can just run headroom proxy. So if I run headroom proxy, it will show all the details, like what headroom, what where it is running, what are like enabled. So optimization is available, enabled, and the caching enabled. So the memory is disabled. If you want, you can able to enable it. For now, it is disabled. So here I have integrated into Claude Code and as well as Codex. So in this both Headroom is already integrated, so I no need to again add it. But if you want to add it, you can follow the same way I've shown here. Uh, yeah, in this slide. So you can define it in this way so that you can able to utilize it. Yeah. There is a error because I've already run the Headroom server. It is already running in my Docker, so I don't need to run it again. So it is already running. I can show you the dashboard here, the Chrome. Uh, okay. The port number is always 8787. If you want, you can change it, but for the default one is the 8787. So this is the dashboard. So in this dashboard, it will show how many tokens you have saved. So this is a live one. So if I run something, it will also make some like there will be a trigger in it. So yeah, this is complete data you can see here. So what exactly the prompt you are giving, if you are using like from where the requests are coming. From open code I have got like 12 requests, and from codex there are like 8 requests, and what percentage of tokens are compressed here. And here you can also see the before and after tokens. So like I have used many like very less in my laptop, so there is very less compression, so like 4K. And I can show you a demo, like I will run it in open code. So if you want to integrate other, like if you want to integrate in your CLI, you can use wrap. So Headroom wrap, and you can give the coding agent which you whatever you want. For now I'm giving the open code, so now it will run in the Headroom. Headroom will be integrated into open code, and now I can give any command and it will run. So I will just give one prompt. Yeah, there is one project. I'll just feed that into open code, and I will give like uh, analyze this project and give me a brief summary. So it is running here, and here also you can see, yeah, here you can see the changes, right? So like 5.4K. So previously it was like 4.0K, and now it changed it to 5.4K. So in this way, the headroom always be integrated here. So headroom is corrected here. So here you can see it. The graph is changed, right? So initially it was 4, now it is like 9.5K. And here you can see the before tokens were like increased after tokens, and there are like 10.9K tokens are saved. So it keeps on like open. You know about open code, right? So open code is similar to the codex and the Claude. So we will be selecting the model, and you just run it. It runs like a codex and Claude. Yeah. So there is also cache rates. So prefix cache impact. So there are like 49.3K cache rates writes in particular like in the headroom. So when there is a similar prompt, if I give some similar prompt which is related to this project, so it will pick from this cache, right? So that it no need to again analyze complete project or do the other like relevant stuff repeatedly. So the redundancy will be decreased here. So here you can see the tokens are like just increasing. And yeah, you can also see the lifetime uh, tokens you have saved. So here the input are like 10 million, and the output are like 10.2K, and you saved like 293 K tokens here. For now, I in my system I have run this, and these many tokens have got saved. So you can also see the historical. So each date, how much number of tokens you have reduced, much dollar, like amount of, like how much cost of date, how much cost you are reducing, everything you can see in this particular dashboard. So this is how you can make things work in your computer. So it's yeah, it runs same. So what it does, everything it is given the summary of it. So there is no any error or anything. So it gives the same as you do in your daily life. And there is also other way you can do it. So which is like programmatically. Here I will show you. Yeah. So I've already written some code. So here from Headroom, if you want to integrate this Headroom in your project, there is a LLM call, or if you want to give data to the LLM from your application. So this is how you can define and use the Headroom. So there is a package called compress within the Headroom. So you have to import it. Then here I have defined the type of uh, data I'm feeding to this particular compressor, and this is the message format. It is a simple JSON format, and here I have given the data. So I firstly I'm giving the log file. You can see the log file contains this much data, and there are errors here. So this is all the log file it contains. And now if I give something like uh, what what the error in this log prompt, so and I'll just run it. So here I'm printing the like how much you can also get the values from here. So result dot token token saved, how much tokens it is getting saved, and before after everything you can make it. So here uh, before tokens were like this much, after it reduced to 10, and then uh, the models it has used like protected. There is some model here. It is used them. I will try with other data as well. So if I want to give this app JSON, so it contains a lot of JSON files here. I'm just feeding this to the compressor now. Mhm. App logs dot JSON, and if I just run, so it reduced to this much. So I think it is getting truncated. It's not showing complete result, but yeah. So before it was like 42,000 lines, and it reduced to 21,000 lines, and there was like 49% reduced. So it is getting truncated, but it has to show other data as well. Maybe because of this. Yeah, this is the complete data. So previously it was huge, but it again reduced. In the JSON as well, uh, the log file will just check the log file. Okay, there are some data it is not giving correctly. Maybe. I'll give the correct prompt, but sometimes it is not given. That's why they are given the CCR, I guess. Here, some log file error files are not mentioned here. Maybe we have to do other. Yeah, just I want to show like how we can do it, but it reduces the tokens, but there are not some necessary tokens that reduce here. So that was a drawback here, I can say. Mm, yeah. And yeah, so it is done, I guess. This previous task which has given in the open code, it is done, and the compression stops here. And you can also use this in your through the MCP as well. So if I give MCP here, okay, yes, here already current model it is set. Just run, we'll start whether it is. I think I've already integrated the MCP, but I will just start. Can you access the Headroom MCPs? Mhm. Okay, code. Okay, we'll try with other agent. So from here, I have just added the MCP server. So you can search the MCP server here. So it will, you can add it. So I have already added it. So yeah, so now my Copilot can able to access MCP. So it is printing the stats. Just ask what the Headroom MCP is available. So there are like three, as I already showed in your slide. So there are three tool calls. So one is retrieve, which can retrieve the original content, and there is a compressor, so which compresses the large content, and there is a headroom status. So I'll just give the data. I'll just give this data to this thing and uh, use headroom compress MCP and identify by the error in this logs. So it is calling the MCP, Headroom MCP. So this is the result written by the MCP, Headroom MCP, and it also gives the error message, only the error messages you can see here. It only gives the error message and it truncates all the data here, and it gives the correct data, right? So there is a two one like error red line. Yeah. So there is a promo code error. Right? So here it shows the keyword promo code. So this is how we can use the MCP. Headroom MCP is also you can directly use it. So there is also much. There won't be much difference in latency as well. So you can use it like daily use. And coming to the next, this is the setup and the how we run into the like Python code I have shown you. So you can also use in your project. You can compress it. Yeah. And the compression and the transforms are like which kind of like a compressor it is using inside. So you can view it here. And coming to the next. So where it will not help you. So Headroom also has some limitations. So here are the some limitations. One is like messages under 300 tokens. So if there are less tokens, you cannot able to compress it because there are already less tokens. So in that case, headroom compression won't be working. And the source code. So if you have a like large source code, and it will just pass through it. And the images, fixed token cost roughly like 1600 each, and the system prompts will be like doing it. And user prompts also, it won't be editing, it will be completely giving the same user prompt. And there are weak return of investment, short conversation exchange. And there is certain cases like when I used in the open code, there is like 4.8% of compression, so that is the like disadvantage. It mostly works on when you have log files or large data. From if you read it from the DB and want only particular data, in that case the headroom will be like top notch, so it can reduce more than 50%. When it comes to the general purpose, it reduces, but it in certain conditions it will just like it cannot able to compress it, as there is as it need to be more how can I say, like it need to keep the data correctly, right? So instead of compressing it, it gives the same data as it is to the model. And next, so here are like some conditions, minimum tokens to crush. You can define it. So there are some metrics. You can make it true, false. So everything can handle at the headroom. So as I told you, if I want to make some changes in headroom, yeah, if I want to disable, enable some features, if I don't want to make keep caching, I can disable it. So everything can do it using headroom proxy. Yeah, these are all just metrics. So you can these are the default values actually. Minimum items to analyze, there are 5. Array shorter than this pass through. So these need to be, you have to be aware of it. So at what extent it will be compressed, and in what extent it cannot be able to compress. So yeah, so I just tried it. So in the Jetson or in Nano, I just deployed the Headroom proxy, and I've also given you all the data. So in your codex also, you have just integrated using the backpack. So first, the pace, like first observe, measure, tune, and commit. So first, we just observed what type of data it is. You can watch in the stats actually. So what kind of data it is getting compressed. So if you want detail, you can also go in stats. There is a JSON format. You can get the data over here also. So these are all request which is given currently. So in open code, I have given some requested. So about this data, the complete like what model it is used, so what kind of tokens we have used, but there is no input or output compressed data, only the overall view, like what percentage of content it is getting extracted, everything stats you can see it in this JSON format. So yeah, and you can measure it, like pick 20 real tasks, run them with without like with and without the proxy. So this actually we have done it previously, and it made some like compression rate is like around 10% or 12%, which I made it. When I tried it for a 1 week, it gives me like 10 to 12%, but we are trying to increase it more. And yeah, so yeah. And four things to remember. Tool output is the tag. So everything in an agent, the tool writes most of the prompt, and every turn resends it. So what you have to remember is, so when a tool call is happening, so the data will be keep on giving the same data. So you are keep on giving the same data, and it keeps on increasing your cost as well. So truncating that data can able to like reduce your cost, and also increase reduce latency and increase accuracy as well. And the truncation is not compression. So in the previous method there is like truncation, right? So it only takes top k previous chart. So instead of that is not only the solution, because we also need the history of it. So instead of keeping unnecessary data in the history, we can just reduce it, so that we can use this like we can use the previous data as well when we compress it. and structure survives, noise does not. So we can emulate noise from the previous history data. And reversible beats aggressive. So if there is some mistake in headroom compression, there is a CCR available in the headroom, so that can able to reverse the changes, and it can help us to like retrieve the original content and make the process work. So yeah, and yeah.